who leads this series, who's not here today, and you notice it secondarily because we're 5 minutes late. Connie is never late about anything. But today we're having 2 talks that have to do with searches. One having to do with Levy flights and one having to do with foraging. But it seems that they're sort of both looking at how do we access information, how do we understand things. The first speaker today is Filippo Radicchi. He comes to us with a degree in physics from the Jacobs University in Bremen. And our second speaker is Peter Todd, who is in the Department of Psychology and Brain Science and received a PhD in psychology from Stanford University. So I'm going to go ahead and turn it right over to them. Filippo?
No, thank you very much. Yes, as today I will talk about some work about searches. Actually, at the end of the talk, you will have more questions than concrete things to say about searches. But nevertheless, this is, I believe, is a nice kind of observation that you can do on, by analyzing just real data. So the starting point is something that is apparently is not related to what I'm going to talk later, and is a lot of basically results about tracking animals in the space. You know, I mean, today with modern technology like GPS or even analyzing videos, you can basically track everything you want in the space. For instance, here there are just a set of animals that you can. That typically are monitored, was position is typically monitored by using GPS devices. So using such kind of data, people publish a lot of papers, also in very prestigious journals like Nature, Science, and so on. And they use they track basically the position and the movements of a large variety of animals, ranging from bears to mammals to fishes, even insects, and so on. So one of the main and surprising results about all these studies is the fact that, in general, the typical pattern that you find when just looking to consecutive position occupied in the space by such animals is the fact that if you just plot the distribution between the distances, where distances are measured in the real space, such distribution obey a power law function. And this is a typical kind of behavior that you observe as what is so-called a Levy flight. Essentially, as you can see from here, the probability that the distance walked between 2 different stages in this kind of exploration of the space decays as a power law with a typical exponent called mu. Now, one of the main results about such kind of works is the fact that this mu, when measured on real data, has a value that is very close to 2. And it's possible basically to make a sort of speculation by looking to this value of mu and studying essentially the behavior of a random searcher in the space moving according to a Levy flight strategy. And when you do such kind of simulation, you realize that if you measure the efficiency, so basically the number of targets encountered by looking for a type in this space, divided by the typical length of the path made in the space, there is a peak. So there is an optimal efficiency for the value of mu equal to 2. Now, of course, you can speculate on this result and say, okay, animals move in the space using such kind of optimal strategy because this is a sort of result of evolution. So only the best animals in the past, best in terms of finding food, essentially, because they're moving in the space looking for food, were able to survive, reproduce, and now today we are able to see this kind of typical pattern in the real world. The question that is one can ask is, okay, this is valid for animals, but what about humans? I mean, if we look to the evolution, we still think about evolution. Also humans, for a very long period of their evolution, were basically foragers. They were moving in the space, looking for food. Only very recently they stopped moving, and they started basically to produce food by themselves. Now, there are a couple of works about still statistical properties of movement patterns of humans in the world. Typically, you can track humans still using a sort of, still using technology. For instance, there is this very nice work by Dirk Brockman and collaborators in which they were able to track people by looking to movements of banknotes. So there is a website called Where is George? Essentially, they were distributing banknotes. And each people that received a certain point, these banknotes were supposed to put the number of the banknote and their position in the world at a certain stage. Now, by looking, by monitoring the position of humans in this way, in this undirected way, when you put all the data together, you are still able to observe such kind of Levy flight pattern. So essentially, the typical distance traveled by humans, it still scales power law with an exponent around 1.5. Another very nice work about still movement patterns in the space is the work by the group of Laszlo Barabasi, in which essentially they monitor the positions of humans on the Earth by tracing them using mobile phones, essentially by looking into the position, depending on the cell in which their mobile phone was attached, they were able to measure their position during the movements. And when you still do the same kind of statistics, so measure the probability distribution between the distances between two consecutive positions in the space, you are still able to see a sort of power law behavior with an exponential cutoff in this case. Now, of course, I mean, one can say, okay, all this kind of empirical data suggests that there is a commonality between animals and humans. So all this kind of, so animals and humans basically share this kind of behavior of following a Levy flight when they move in the space. Now, there are a couple of problems. First of all, I mean, if you look really carefully to data, the results about Levy flight in animals are a little bit controversial. Actually, the main result in this paper was the fact that animals are able to change from a Levy flight behavior to just a random walk behavior, depending on the density of the food in the environment, essentially. When the food is very dense, so they have a lot of resources, then they switch to a Brownian motion. And then there are also a series of problems that regards data itself. First of all the data that I showed you before, all these kind of results, are results obtained by aggregating data. So you are not really monitoring individuals, but you are monitoring the population. Now, you are not sure if this kind of heterogeneous behavior is a result of the aggregating process, so basically it's a heterogeneous population, or it's just, or is given by the fact that individuals really follow an heterogeneous pattern of distances. Another very big problem is about the scaling, because power law should be monitored over a certain range of values, order of magnitudes, and typically in this case, 3 orders of magnitudes represent really a luxury. So it's very hard to find movements longer than 3 orders of magnitude. And then if you think about tracing humans today, I mean, they are not really searching. They're just moving in the space. They go to work, they go to school, I don't know. So you cannot really establish a sort of parallelism between animals and humans. So such kind of analogy, actually, we found some kind of very nice result by looking to data that apparently are not related to search, to movements in the space. And that data coming from this special kind of online games that are called lowest unique bid auctions. Essentially, the idea is like you have a very big prize, like a sport car, an house. Then you can bid between 1 cent and $1,000, for instance. And you have a resolution of 1 cent. So you can bid on 1 cent, 2 cents, and so on. Each time that the player places a bid, he has to pay a fee. The typical fee value is like $20, depending on the on the price that is up for auction. And the point is that, of course, when you bid, when you play to this game, you don't know anything about the others, what they are doing. Now, the winner is the one that made, at the end of the auction, the lowest and unmatched bid value. Like in this case, a particular situation, you have, 3 persons bid on 1 cent, 2 on 2 cents, only 1 on 3 cents. There is also only 1 person that places a bid on 5 cents, but this is not the lowest value. So mathematically speaking, you can imagine that the space in this case is just a unidimensional lattice in which you have different sides given by 1 cent, 2 cents, and so on. The typical value of the goods that are up for auction is very high, from $1,000 to $100,000. The nice and interesting thing of this kind of that is the fact that the agents really are moving independently in the space. Now, if you think, while playing, the position of this target, the lowest unique bid auction, is changing according to the movements of the bids placed by the players. Of course, the target is just one, and the range is very big. So the resources in this case are very scarce, right? The density is very scarce. And the other nice thing is the fact that everybody is playing independently, so you can basically model any agent as an independent forager, somehow. So we collected data from different websites, and the nice thing is the fact that you can really reconstruct the trajectory in this bid-based exploration by looking, you have a unique member IDs, bid values, and timestamps. So when you do some statistics on that, like in this case, you can just order bid values according to the time when they did it, so just first, second, and so on. And this is more or less what you observe. This is just a single individual in a single auction. But then, of course, you can also take the difference between the bid values, the absolute value of the difference, and measure the change. You see that there are typically the typical pattern that you observe are very, very small changes, but from time to time, very long jumps. When you put everything together, you measure the probability distribution of these bid changes, you observe a power law decay. So one nice thing, as you can see here, is the fact that you can measure this power law decay over 4 orders of magnitude. And it's also very clear from this kind of plot that is a power law decay. So we performed some statistical tests about really measuring the power law behavior at level of individuals. And this can be done just by maximizing the likelihood that what you observe is compatible with the power law. Typically what you find is like, there are some cases in which essentially the behavior is not statistically compatible with the Levy flight behavior, but the majority of the cases, the p-value, what you can measure, for it's very high. One interesting thing is that, of course, in this case, you can monitor the power law behavior, so this kind of Levy flight, for every individual. So what you can do is like associate to each individual in each individual auction, you can associate an exponent. And then you can do a probability distribution for the exponents. And this is the result that you obtain. So you see that there is a clear peak around the value of 1.2, 1.3, more or less. So it seems that basically everybody is using not only a Levy flight strategy, but also more or less the same exponent. And the question is why? So this is also true if you monitor essentially, if you aggregate data in this case, of course. So if it's true for individuals, it's true also for the entire population. You see that essentially this kind of behavior is true for different websites, different sources of information about this kind of lowest unique bid auction. It's true if you monitor positive and negative changes. So if you bid on higher or lower values, essentially. It's also true if you monitor different users with different activity levels. like people that place only less than 10 bits or more than 200 bits in a single auction. And it's also very robust if you look to the stage of the game. Like in this case, if you just monitor the change between 0 and the first bit value, or between the last two bit values, you see that still there is this kind of power law behavior, and the exponent is very robust. Nothing, just if they are winning or not. Generally not. No. So what you can do is like you can try to model this kind of behavior because, as I just said, any individual is any agent in this auction is an independent explorer in this bit space. So you can, for instance, make a very strong assumption, but of course is supported by the empirical evidence. So each user will choose a bit value in this space by using a power law function. You can imagine, I mean, in this case, there is a sort of bias going towards lower values. So you can imagine that everybody starts at position equal to 0. And in the simplest case, imagine that everybody can just make a single bid according to this power law distribution and jump from 0 to a given value according to the distribution. So you can, in principle, model for a given number of players, a given set of exponent, you can calculate a sort of probability distribution for the configuration. So the fact that you can have, I don't know, one bid on 1 cent, 2 bids on 3 cents, and so on. But you can make some kind of simplification by using the fact that everything is completely independent. So you can measure, for instance, what is the probability that a bid made on the ith value is unique. So if you imagine that you have n players, everybody playing with the same strategy gamma, this is given by this simple expression. Essentially, the probability of making this bid times the probability that no one else will place a bid on that value. So this is the probability of being unique. Of course, you can calculate also the probability of being, of selecting a lowest and unique bid in this case. Imagine that you have a single player playing with strategy beta against a population that is playing with strategy gamma. Beta and gamma are just exponent of the power law of the Levy flight. So the probability that this player playing with strategy beta will place the unique and the lowest bid value in a given auction is given by this expression. So placing a bid on the value V times the probability that no one else plays a bid on value V, because it should be unique, times the probability that no of the values smaller than V are unique, right? So you can calculate, I don't know, the probability that this agent will win the auction. You can calculate the typical value of R winning bid. You can assume also then to repeat this kind of case an infinite number of times and calculate essentially the economic return. So if I'm a player playing with strategy beta against a population that is playing, of n players playing with strategy gamma, my economic return is just given by the probability of winning the auction times the value of the object, because it's what I'm getting from the auction, minus the typical value that I pay for making this auction. Of course, I mean, if this value is larger than the fee that I have to pay for making a single bid, it's convenient for me to play. I have a positive economic return. Otherwise, it's not convenient. You can extend such kind of calculation also to multiple bids. So everybody's placing more bids. But one nice thing of this kind of model is the fact that when you solve the numerical equations, you find this kind of payoff matrix. So this is on this, the color means just the economic return that you should still compare with the cost of the fee. And this is strategy beta of the player against the population with strategy gamma. You see that around 1.2, 1.3, you have a saddle point that in the payoff matrix corresponds to a Nash equilibrium. So it's an optimal strategy. So the main point is that in this case, players are playing with that particular strategy because that strategy is optimal. You can also extend such kind of thing to not just to a static game, but also in a case in which players can evolve. So change strategy, copying strategy of the winners is a sort of Moran-like model. Of course, they always converge to the Nash equilibrium also in this case. But one point that is interesting about this data, of course, is the fact that everybody's playing more or less using an optimal strategy, but playing the game is not optimal. For instance, if you just see, I mean, for the winner, it's very convenient to play. You see, this is the relative cost of the winner as a function of the value of the prize that is up for auction. So each time that you play, you have to pay these fees. As you can see, if you win the auction, at the end, you pay more or less half price for the prize. But of course, this is valid only for the winner. Of course, for the auctioneer, it's very convenient to organize such kind of games, because typically they double the value of the prize. But since you have this kind of inequality, everybody's playing with the optimal strategy, of course, the economic return is always negative. So we have always this kind of inequality. So everybody's playing with the optimal strategy, but playing is not optimal. Also, I mean, as you can see, everybody more or less is using the same strategy. So at the end, the probability of winning is just 1 divided by the total number of bits that you play. So it's a sort of lottery. And this is why this website were closed. So you cannot any longer find data about these auctions. You can download from my website if you're interested in that. But I mean, and so going back to this kind of original question, I don't know. This is, of course, is the first step, try to understand how people really search, at least in this very special kind of environment. But we are trying to organize some kind of experiment. Actually, together with Ryan, we developed, together with other students, a very nice website in which essentially you have a two-dimensional space, and people can click and look for random hidden targets. And so far, some results are encouraging, because if you measure now the distance between consecutive clicks, and the distance is measured like just Euclidean distance, depending on the pixel, you see that there is such kind of long tail behavior. Of course, also in this case, one of the main problems is that the screen cannot be so large. So the order of magnitudes that you can monitor is not as broad as in the case of lowest unique bit auction. So let me just conclude by thanking my collaborators on this project, Luis Amaral and Andrea Baronchelli. This is a list of key publications on this work. Thank you very much.
You didn't mention N. I guess this probability strongly depends on how many people play.
I didn't mention because I went too fast, but if you look to the slides, of course, it's a parameter. Because if n goes to infinity, you cover the entire space, no one can win. And in the solution of this, in the numerical solution of the question, I set n equal to the typical value that you have in the auctions. So around 150, more or less. Now, of course. It changed with n, it changed also slightly, you see, with t, total number of bits per player is moving on the right. So essentially, what I expect to see is like if n goes to infinity, you have just same color. So you cannot win, essentially. You have 0 probability of making a unique bit, essentially. Right? If you play alone, the best strategy is to place a bid on 1 cent. Yep.
Think about optimal strategy fixed budget?
Well, what we did in this kind of approach was that everybody's placing the same number of bits, so they have the same budget. But in principle, this is not a realistic assumption because also budget aspect is distributed according to some law. And of course, things can change. Yeah, I agree with you. Other questions? Okay.